Hello, my dear students. Welcome back to this next session on industrial metallurgy. These are the contents that we'll cover in the session 12. This flow diagram I had shown to you in the last session. And you see here we are trying to show that what type of phases exist in alloy systems when the classification of phases is done on the basis of the properties or the characteristics that they show. And it was discussed that there are two main types of phases. You can have either the phase that is existing in the material system would be a solid solution, and we had also said that at least one of the phases that is seen in an alloy system must be a solid solution. And if you see a phase which is not a solid solution, then it is an intermediate phase. And then we had gone on to say that solid solutions are further of two types and intermediate phases are further of three categories or three types. Now let us discuss them one by one. You see, I have already discussed with you what is meant by a solid solution. And it was said that solid solution is a solution in the solid state in which atoms of the solute element do not damage or destroy the crystal structure of the solvent element, but they become a part of it. But then these solid solutions are further of two main types. Solid solutions can be substitutional solid solutions, or then they will be interstitial solid solutions. What is a substitutional solid solution? You see, in a solid solution, if the atoms of the solute element, here the atoms of the solute element have been shown in red color and that of the solvent element has been shown in blue color. This shows the formation of the solid solution, that when a solid solution has got formed, when the solid solution has got formed, this is how its unit cell is looking like. We have taken this example. Now you can see that solvent was having BCC crystal structure, and this is the unit cell of the solvent. And it was assumed that solute has got FCC crystal structure, and this is how its unit cell looks like. And this is the final solid solution. Now, this final solid solution is substitutional solid solution if at some of the lattice positions you see that solute atoms have substituted or replaced the solvents atoms. So the crystal structure would be that of the solvent element. That is always true for a solid solution. So if a solid solution is getting formed between two elements or even more than two elements, then the final unit cell that would be seen in the solid solution will be of the same crystal structure as was of the solvent. The difference is that whereas in the unit cell of the solvent only atoms of the solvent element were present, in the final solution elements of atoms of all the constituent elements would be sharing the same type, same unit cell, same crystal structure. Now in this case we have assumed that there are only two elements, solute and the solvent. So what I'm saying is that in a solid solution, if the atoms of the solute element substitute or replace the atoms of the solvent element at some positions in the crystal structure of the solvent element, then the solid solution that gets formed is called substitutional solid solution, as is the example that is showing over here. Now let's come to the next type of the second and the final type of other solid solution that can get formed. That's called an interstitial solid solution. So in an interstitial solid solution, the solvent elements crystal structure would be seen in the final solid solution, but now the solute atoms will not substitute or replace the solvents atoms in the crystal structure of the solvent. The crystal structure of the unit cell of the solid solution would exactly be the lattice positions would be occupied by the solvent element as were they being occupied in the solvent when it was all alone. So even in the solid solution, all the lattice positions are being occupied by the solvents atoms. But then there are going to be some solute atoms also according to the weight proportion that had been taken initially for the solute and the solvent. But then these interstitial, these solute atoms would occupy these interstitial positions, which we popularly called voids or interatomic spaces, because the unit cell contains a large number of voids like octahedral voids, and there are so many other vacant spaces present in it. Now here you can see that the solute atom is occupying one of the voids that is present in the crystal structure of the solvent element. So if a solid solution is getting formed and is getting formed in such a manner that the that the solute atoms are not taking up or replacing or substituting the solvent atoms in the crystal structure of the solvent atom, but in the crystal structure of the solvent atom they are occupying randomly interatomic spaces or interstitial spaces, or they are occupying what are called voids, then the solid solution that has got formed is called an interstitial solid solution. But students, mind it, there might be a lot of vacant space present in the unit cell of any element, any solvent, but the path through which this vacant space can be taken, those paths are very constrained. The openings through which an atom can go and reach a void or a interatomic space, those paths are very constrained, very narrow, and it's only very small sized atoms. And you can clearly see over here the size of the solute atom is very small in comparison to that of the solvent atom. So since the path, the openings through which voids can be reached, they are very narrow and constrained, only very small sized atoms can act as interstitial solutes. And there are only a few examples of elements like boron, carbon, nitrogen, whose atomic size is very small, and they can act as interstitial solutes in the formation of interstitial solid solutions. And in a, as such, a general rule says that if the size of the atoms of an element is less than 1 angstroms, then only it can act as an interstitial solute in the formation of an interstitial solid solution. And that's what we would be discussing with you in the next slide. So in the next slide, you can see that here we have written what is the condition, or what are the conditions for the formation of an interstitial solid solution. And I've discussed this entire matter with you. And I also said a while ago that boron, carbon, nitrogen are the only elements whose atoms are small enough, smaller than this size, to act as interstitial solutes for solvent metals. Steels being the most important example, where carbon gets interstitially dissolved in all types of iron, gamma iron, uh, delta iron, alpha iron, etc. So in this example we have shown that in a steel component, carbon atom is getting dissolved in gamma iron and forms a phase called austenite. We'll discuss it in the lectures to come. See, there can also be examples where you have 2-3 elements forming a solid solution, and you can see here iron atom is the solvent, so the crystal structure is that of the solvent. But then as solutes you have taken carbon atom and manganese atom, and you can see that in the same solid solution, one of the elements atoms is acting as a substitutional solute, whereas the other is acting as an interstitial solute. So in multiple component systems, you would see that the solute atoms may substitute also the solvent atoms at some of the lattice positions in the solvent elements crystal structure, and some of the elements may come interstitially also. Okay. So thanks for watching. We'll continue with what are called intermediate phases in the next class. Thank you so much. Thanks for your patience and thanks for watching.